were necessary. And you might say, well, perhaps then these case histories themselves are sufficient for us as a profession. We could read the expert reports from these case histories and say, well, this is enough of a tutorial for us in consulting to go forward with these numerical methods. And really that is not the case, because the problem is this. What you're looking at here is a cross-section of the Cadia Dam and the Cadia failure. And the failure was driven by what I'm highlighting in the bottom, which you can see in yellow. It was actually strain weakening in behavior in the residual soils in the foundation. So although the thing liquefied, and there was an interplay between the development of liquefaction and the way the foundation behaved, it was a very complex situation. And this is true of most of our famous liquefaction cases: Fort Peck, Nurluk, Los Frailes, Mount Polly, Fundao, Cadia. They have a lot of things going on, and they are not simple liquefaction events. And if there are a lot of things going on, you can have a range of views over what is the truth, and that's not much use to you as a validation case. So why the interest in Tar Island? Well, what we have in Tar Island, and you can see the cross section here, it started out, as most of you know, as a conventional dam, and then they found the tailings were not consolidating as expected. So there was a rapid change to upstream construction, and the dam had to go way higher than initially planned. And the guys were learning how to do upstream construction and work out in stages onto the previously spigoted beaches. And so as part of that, they had a number of slumps, and these were, you know, okay, I'm not sure where I lost you all, but hopefully we can continue now. The interest in Tar Island was that it's a simple dead loading event, and it's got reasonable data, and it's documented in a very nice paper, Liquefaction Considerations of the Suncor Tailings Pond by Plures, O'Neill, McRoberts and Chan. And that paper forms the starting point for our analysis, or our setting things up. We have quite a nice set of documentation. And as I say, it's almost like a test fill. In fact, you could regard it as a test fill. So it's really rather good for us. In terms of where it is, and those of you in Alberta, I'm sure this is engraved in your hearts. This top right photo is from the day when they were starting. So this is, I guess, probably about 1973. And that's where the Tar Island dike is going to go up here. And this photo on the bottom left is the dike, I guess, 10 years ago, at which point we're up at about 100 meters and we're heading towards closing it out. So it's quite a substantial structure, but our story, or the analysis, is in these very early days when the guys were learning how to do upstream construction. And what they had was 4 slumps, and they were testing things out. And they plotted up the height of the fill versus the rate of construction. And this is kind of norm for upstream construction. They've developed a rule for if you stayed out of that shaded zone, you could go successfully upstream. And that was procedures they established, and they established procedures continued for, as I understand it, without much change the next 40 years. In the early 70s, they did some laboratory strength testing, but there were no CPTs. Indeed, there were no CPTs physically in Canada in 1974. Since 1990, we've actually accumulated reasonable number of high-quality triaxial tests. We actually have a cone calibration chambers tests, and we have got lots of seismic CPTUs. So in pulling this case history together, we're actually blending original documentation from the day with measurements made 20 years later, but we're relying on the idea that the placement procedures are the same. The sand has remained the same. And that is our justification for why we say we can take more recent data and map it back to what was happening in 1970 to understand why things happened as they did. Now, one of the most, or a remarkable feature of this failure, or this slump, is if you think about it here, and this is the rays we're going to look at, if you analyze that with a slip circle, limit equilibrium slip circle analysis, you'd find the movements would occur quite close in. But they actually reported movements extended quite a long way away. And this is a very unusual aspect of the case history. This, I'm taking you now in these photos 5,000 miles away from Alberta. We're actually here in Portugal. And here we were building out arrays onto tailings, much the same as happening at Tar Island. And this is only a 2.5 meter raise. It's only a fifth the height of Tar Island. And the dozer got too close to the edge and triggered a liquefaction failure. What I found staggering, because that's me witnessing this thing, is just how far upstream it extended. It was far from what you'd expect of a simple rotational failure. Now, that sort of influenced, shall I say, my view that, yeah, this is interesting and real. What I'd have liked to see in the Pluis et al. Paper, and I've not seen, and maybe some of you listening may know some of the history, but I'd like to be told a bit about going out in rubber boats and sounding where the tailings had moved. A little more detail would have been interesting, but when you're looking at all these case history papers, you must, at first instance, assume the authors are reporting accurately. So we said, okay, this gives us a bit of confidence, and this is an unusual aspect to the failure. Now, before I get into Plaxis and modeling and what we're up to, I do need to tell you a little bit about critical state theory. A goodly few of you who've heard me talk before have heard 1 hour talks on critical state theory and where it comes from. You'll be glad to know I'm not going to impose that on you this afternoon, but I do need to bring a couple of things out. The first thing is when people hear the words critical state, they automatically assume you're using CAM clay, and that is not the truth. The folks at Cambridge, the original CAM clay or modified CAM clay, they put the mathematics, shall we say, together in a first coherent way. But the idea is actually traced back to the Corps of Engineers. And this dam, which is Franklin Falls Dam in New Hampshire, it's about an hour up the turnpike from Boston. And in those days, the liquefaction was called sand flow failure. And there'd been a rash of liquefaction failures in the States in the period from about 1895 through about 1920. And the engineer of record of this dam was a chap called Colonel Lyman, and he was determined his dam was not going to suffer sand flow failure. And what Lyman did, he looked at this notion, which you see in the bottom left, and this is actually, this idea was introduced by the chap Reynolds. Reynolds number in hydraulics was the same guy. And he said, well, if you idealize soil as particles, and you can look at sand under with your eye or a magnifying glass, you can see that's a reasonable starting point. If the packing you see on the left is a face-centered cubic, and that's the loosest theoretical arrangement you can have. This one over here is body-centered cubic, it's the densest possible. And what he said was, if those lattices are going to be deformed, this one is going to pack down, that one's going to have to expand so the particles can ride over each other. So volume change, or a tendency to volume change, is intrinsic to the deformation of soils. And there is an effective void ratio. If you're loose, it'll tend to be contractive. If it's dense, it's going to be dilative. And Lyman took this idea and got a bunch of shear box testing done. So we have a direct shear box here. And they did this with dense sand, medium dense sand, and loose sand. They got different stress strain curves, which you see here. And they then found that the void ratio evolved, which is what you see here with displacement. But you got to the same endpoint. And the endpoint was called the critical void ratio because they came to the view that if the thing was tending to dilate, then if there's pore water in the sand, the thing would be negative pore pressure and it will be safe, and that there would be no sand flow failure. So it was called critical because that was the critical construction decision. And then what they discovered very rapidly thereafter, because when it was first introduced, they had in mind that this was going to be like an E min or E max, just a single value. But it was rapidly found that the critical void ratio varied with confining stress, which is what you see there. And this is a canonical figure. This is Casa Grande, who pulled it together, although a lot of the testing was actually done by Don Taylor. Now, what we do in critical state theory, and you can see Casa Grande has labeled, this is his labeling of A to B to C. That is the sequence which he's thinking. So we have a stress strain curve, and magically that stress strain curve is somehow associated with a change in void ratio that magically somehow produces a unique critical state. Now, what we say in critical state theory is actually Casa Grande has got this wrong. The diagram should be read from here to here to here. That is, we have a unique critical state line. And it's unique because basically it's a kinematic process. For any particular stress situation, there's only going to be one packing where these particles can freely ride over each other. It's kind of like a birth-death process. Some particles will be dropping into void ratio space, others have to be dilating out of it, and it's a dynamic situation. And it's for any particular gradation, any particular grain shape, you get this unique line. So we say, okay, we're going to take that as an axiom. And the nice thing about a unique endpoint, it means the mathematics or our applied mechanics is well conditioned because we know where we're going. It's very easy. And the way we can say we know where we're going, we can say actually, if we define a deviation measure, so that is our current void ratio, and we subtract from that the void ratio in the critical state for the current confining stress, and we call that the state parameter. This whole framework can be represented by the statement that the state parameter goes to 0 as the distortion goes to infinity. And that captures the essence of Casa Grande's thing. And the neat thing about that is, and we treat that as a second axiom, that the state parameter goes to 0 as the distortion goes to infinity. And the nice thing about that is we can then do some mathematics around that, because we've now taken a sketch from a geologist, and we've now said, well, actually, we can characterize that properly and formally. And once we've done that formally, we can then turn mechanics loose and we can derive a few things. And then what we get out of this is actually the stress strain behavior is the result of our derivation. It's not the start. Okay. This is what it looks like. And this is critical state theory in one slide. What we have on this left-hand side here is a familiar PQ plot, except we're now using it in terms of stress invariance. So it's a true 3D stress invariance over here. And it's in effect two plots on top of each other, because you notice down here, I'm plotting, I've labeled the axis volumetric strain increment. Over here, I'm called distortional increment. So I have, I have two graphs laid on top of each other, or two plots laid up on top of each other. And the reason for this is we're actually going to rely on the dissipation of plastic work. And you don't get a free choice on these invariants. What we have in the jargon mechanics, these have to be what's called work conjugates. So if I take this mean effective stress here and multiply it by that strain increment there, and I take this deviatoric stress here and I multiply it by the corresponding deviatoric strain increment, the addition of those two multiplications is the total work going into the system that's being dissipated plastically. And the reason that's important is I can then invoke a theorem, and the theorem tells me the relationship between the strain increment vector. With this vector here is the ratio, the bottom is the volumetric strain increment, and the vertical bit is the deviatoric strain increment. So the ratio of the strain increments is a vector, and there's a theorem that says the yield surface will be perpendicular to that vector. Now, if I know that gradient from stress to latency, then go away, then I can integrate, oh yeah, excuse me chaps, then I can integrate and derive the shape of the yield surface. When you do an integration, you get, you're required to an integration constant. Well, we choose this constant here. Why do we choose that? Because the strain increment vector is going to be perpendicular, it's going to be going vertically upwards, which means I've got no volumetric strain. Well, that's one of the conditions of a critical state. So the idea then is simply, well, okay, if that's one of the conditions, then remember the axiom is the state parameter goes to 0, or everything goes to a critical state with distortional strain. We then say, well, the hardening law is obvious. Orange dot moves to green dot, and green dot is the critical state for that particular void ratio, which comes across from this diagram here. So where does the state parameters fit in? Well, like this. Theoretically, there is a relationship between the limiting dilation rate and the state parameter. And again, this is a mathematical derivation. And we implement that by using that to control where the hardening point is. So our image condition. So this brings the whole shebang together in a simple framework. Where does CAM clay fit in, just out of a historical reference? CAM clay simply puts orange dot on top of green dot at the get-go, and they choose a hardening law so orange dot remains on top of the green dot as we go forward. So this is a generalization of the ideas in CAM clay, and CAM clay exists as a special instance of this. Okay, so that's a fancy looking pictures, and there's nothing worse than looking at equations on the screen and trying to get your head around them. What I'd like to emphasize or put in front of you here is these equations are very simple. This is that picture you've seen before, and all those yield surfaces moving around and everything is done by 4 simple equations. And you can see from the form of them, there's nothing difficult about these equations. And if there's any catch in it, it's that they have to be solved simultaneously. Effectively, that precludes you from closed form solutions, but it means that numerically, it's not very difficult at all. And I also like to make the point that these ideas are quite old. There's always, in a plasticity theory, you always have a flow rule, which is, which way is the material moving, north, south, east, west, etc. The yield surface is just the conditions when plastic strains develop, or if you're inside the yield surface, you're elastic only. And hardening rule is more subtle. That's about how the yield surface evolves with strain. And you always have those 3 elements. But as you can see, the equations are straightforward. And they go back many, many years. I'm going to introduce the properties that go with these equations as we walk through now. But this is the entire property set in front of you on the screen. And a couple of things I want to make to you. The properties are very simple. There's no funny derivatives or anything. This is things you can just plot up in the lab and you can pick up the properties. But the key thing is that properties are independent of void ratio. And that means we can use disturbed samples as well. So it's very, very easy to reconstitute samples and measure what we need to know. To bring you to back to the particular case of Tar Island, we have 4 critical state loci that I have access to, and these are they on the screen. We're plotting here void ratio versus mean effective stress. You can read that. The blue lines are from the day of the early days of Suncor. These are Suncor tailings tested circa 1974 thereabouts. 5% fines and 30% fines. The Mildred Lake one is the one we did a lot of testing on, we then being Golder, and Albion is more testing by Golder, which we've got more modern tests, which we've also got to critical state lines. The parameters, I said I'd introduce parameters to you, simply the slope of these CSLs in a log on an E-log-P plot is the parameter lambda. We subscript it 10 to say it's defined on base 10 logarithms. Gamma, which I don't have on the slide, is simply the altitude intercept at 1 kPa. Interestingly, it's helpful to think about how your materials stack up compared to the experience database. And what I have on this second plot here is this property lambda 10 plotted against fines content, and there are 30 different soils on this plot. Over here, this is our standard laboratory clean sands, the Ottawa sand, the Ticino sand, where we've stripped all the fines out of it. Over here, we have some regular construction sands that you and I in consulting might encounter, and then we get over to some sandy silt tailings over here. The blue dots are the values for oil sand tailings, and the only one that the Suncor, the Mildred Lake, and Albion are, much of a muchness compared to what you might expect. The funny one out is the Suncor at 30% fines, which seems to be unusually incompressible. Okay, going further. In terms of strength properties, what we do is we do ideally drain tests on dense samples, and each of these diamonds is a drained traxel test on a dense-ish sample, quite dense over here, less dense over here, and you just plot the peak strength versus peak dilatancy. Because we have a compression positive conventional soil mechanics, peak dilatancy is actually the minimum value of the parameter D. And remember, I was talking about work conjugate invariance, or you don't get a free choice on how you measure dilatancy. It has to be this volumetric strain invariant divided by the distortional strain invariant. So you need to keep your wits about you when you calculate that. And rather than doing peak friction angle, we do everything as a stress ratio. So that's Q over P. And so it's the peak value. And you get a straight line through the data. MTC is by definition the intercept at d min equals 0. And the slope is something less than 1. This idea on this plot was introduced by Don Taylor. And then Alan Bishop put the equations to it. And they called it the interlocking model, looking back to Reynolds and the idea that the soil particles had to ride over each other, and the degree of riding over required was called interlocking. If the Taylor-Bishop idea was perfectly correct, that line would have a slope of 1, and the answer is when you plot up data, it usually doesn't. Nova came along, and he suggested that actually not all of the volumetric work gets shifted across to the distortional behavior, and that some of it is dealt with volumetrically itself. And he said the proportion going volumetrically was n, so thus 1 minus n is the proportion that goes to distortion. Commonly, n is in the territory of 0.35, give or take. So about a third of your work going into the sample is heading into the volumetric component rather than going into distortion. Now, this is a very nice strength model, and you see it's quite predictive and so forth. But you've got to know what d min is. So, okay, where does d min come from? Well, that's very simple, because again, if we plot d min here and we plot it against the state parameter, remember that void ratio offset. So this is the void ratio offset at the instant of d min. Again, it's a theoretical expectation that it should be a straight line going through 0. And that, you see, our data from our oil sands, that is indeed what we get. And the parameter chi, this is, I should have mentioned here, the convention is that properties in critical state models should be uppercase Greek. Obviously, lambda 10 for some reason isn't, but we try and stay with this convention of our properties uppercase Greek. So even though that looks like the letter X, in fact, it's a capital C in Greek font, or Greek capital C. And that's the property chi. And again, it's just a slope. So you can plot up a bunch of lab tests, and you got your properties. Here are the properties we came up with for Tar Island. This is the ones here, the Tar Island 5%, Tar Island 30%. These were measured in the day. So this is data you can find in the Plewis et al. Paper. They didn't do any dense tests, or that I'm aware of, and they certainly didn't plot up any dilation stuff. So we're unable to pull off N and chi or chi from their data of the day. So we looked to Mildred Lake. We're quite similar over here, and we actually have good definition of N and good definition of chi. Albion, it's for some bizarre reason, the M seems rather higher than the other stuff. So what we said was actually, we will run with the Mildred Lake to supplement what we see over here. So that's where our parameter set came from. Gmax, because we haven't mentioned anything about elasticity yet. Elasticity comes from seismic CPT. Before I get down to elasticity, let me just show you how well this whole scheme works. That's a dense test on Mildred Lake sand, And that's a fit of our theory or our constitutive model developed within the generalized critical state theory, which is Norsand, and that's the blue lines. And what I want you to notice over here, we have exact honoring of the void ratio. If we shift to, I should say I haven't, I've got to introduce this property H, which is our hardening modulus. We don't quite use it like this, but to get your heads around what this soil property H is, it's like a normalized initial stiffness in a track test. So initial tangent stiffness when you load it, that's what H kind of means. If we switch to loose sand or loose test, again, you see explicit honoring of void ratio and a lovely, lovely match to volumetric strain and stress strain behavior. And going from dense to loose, I'm not changing properties. What I'm changing is just simply the state parameter or void ratio. And that is the offer and the attraction of critical state theory. It gives a mechanical linking of void ratio to mechanical behavior. Now, elasticity. We have scads and scads of Gmax data in situ. As I'm sure many of you are aware of, the seismic cone has almost become the weapon of choice for our site investigations. And it's virtually free data. And this is a bunch of data. This is actually from Suncor, from the Tar Island site, or this is obviously later. And the green squares are values in the compacted cells. The orange or yellow diamonds are beach above water, and the blue dots are the beach below water, which is our key player, which I'm going to introduce in a moment when we start looking at the idealization. I've thrown a couple of guidelines on here, which are called Erksack sand. These gray lines are from the elastic model we got after a lot of calibration work with Erksack sand. And so that tells you if you've got a dense and particular void ratio and it's loose, this a much looser void ratio, that is the sort of behavior you expect. Now, we've actually used in the Plaxis model, we went for a slightly softer base case, which is this thick line here. Why did we do that? Well, when we do pressure meter testing, an unload reload cycle of the pressure meter is theoretically twice the Gmax. And you can pull off Gmax from the pressure meters. And when I've done that, and I've done a fair few of it, it always seems to be a little less than the geophysical value. Now, keep in mind when we use seismic methods, we're testing at something like 1 kilohertz, which is a pretty high frequency for soil response. Where we test with the pressure meter, we're testing at strain rates consistent with our loadings. So I felt, or we felt that, it's royal we here, that as a engineering judgment call, we will take our base case for our Plaxis model as the lower bound to what we actually measured with the seismic shear module, or the seismic CPT. Pulling all this together, how does our fit using this somewhat elaborate process of looking to mold or relate to supplement what we haven't measured in the day? How does it all come together? Well, the pink stress strain curve is from the Pluis et al. Paper. The blue curve is what we compute for this particular test using the calibrations I've just run you through. And I find that quite a pleasing match, particularly as it's 45 years ago. So we've got ourselves an understanding of soil properties and the stress strain behavior. But remember, I showed you how the stress strain behavior changes depending on the state parameter. So we've now got a question. Okay, we know what the properties of our Tar Island sands are. What are we going to do about assessing the in-situ state? Because without knowing the in-situ state, we're not going anywhere. Now, this is where the Corps of Engineers ran into a problem back in the late 30s and 1940. They essentially came up with a laboratory understanding with their shear box testing, but they had no real way of getting to what on earth the in-situ void ratio was. The great Canadian contribution to this critical state theory was that we mapped the state parameter in situ through the CPT, and we did a lot of work around this, we being primarily Gulf, but also ESSA Resources Canada, and Dome Petroleum as it was then, and then EBA and Hardy and Golder were all involved as well. So there was a big group in Calgary, or a group is fair, an association of people in Calgary in the 1980s who really pushed this. This, as a bit of a historical note, the chap holding the cone you see in the picture, at the time when I was first introduced to the CPT, which was in 1979, you borrowed it from National Research Council in Ottawa, and it was a horrible strain gauge instrument with wires coming out the top of it, and you had to go and rent a chart recorder and nothing calibrated. Well, here am I working in hydraulic fill construction for Gulf, and I'm with an oil company. We have money. So we actually commissioned and had this high quality CPT built for us. This is the first digital CPT brought into Canada. This is in 1984. And we have a downhole analog to digital. We have downhole thermal compensation, yappity yap. It was a superb piece of kit. And not only that, we have digital transmission to the surface, and we then recorded it. And the little computer down the bottom you see that was our data acquisition computer. And Gulf wrote the software for the data acquisition and processing. And because I like the proverb, trust is wonderful, distrust is better, when we first started using the device, and the reason this chap, Leonard Johnson, is holding the CPT is I wasn't going to my construction site in the Arctic with some CPTs he shipped me from Sweden. Oh, no, for our money, he's coming with them. So if anything went wrong, he's going to repair them right there and now. So anyway, that's how we got into using the CPT. And what we find is theoretically, and I'm going to demonstrate where the theoretical comes from in a second, the normalized tip resistance, which is QT minus P naught over P naught dash, is a very simple exponential function of the state parameter. K and M are soil-specific properties, and you have a very simple equation. You can, of course, invert it so the state parameter is just log of Q over K divided by M. And a bunch of you will be familiar with the NCER method and looking at liquefaction. I emphasize to you now that with critical state theory, there is no fines content correction. We have material properties, K and M, which are related to the H's, the Chi's, and the M's and the N's, the actual mechanical properties. And we have no reference pressure normalization. It has to be done as a simple stress ratio, which is this Q. Okay, I'll come back to the theory in a moment. Let me just show you what some of this data looks like. This is a sounding in Suncor, and it's from a campaign by KCB, Clone Crippen Berger, and this was, I believe, this was done in 2011. So he's desperately looking for a date on the slide, and this is from a beach above water, upstream of a cell, and this is a kind of a fairly typical thing. And it's basically drained, but you see it's a couple of glitches. We have put these glitches down to residual bitumen contamination because we get a thing. Curiously, you can see here they get negative excess pore pressures. There was a little slight positive kick there, but the contamination seems to bizarrely be slightly dilatant. Now, back to the model and what we're going to idealize. This top right chart schematic is from the Plewis et al. Paper, and they identify two material types. They've got what they call beach sand overboarded into water, which is what we now call beach below water. And then they had, on the, as you can see here, they said previously overboarded sand. We took that to be something which was spigoted onto beach, and it was what we now call beach above water. And it's now become buried as the pond level and the dam has been raised and the pond level's gone up. And they have this very clear line in here. So we said, okay, given that we ought to respect their paper, and they presumably had a good reason for putting that beach in there, we would like to pull out from the investigation done in 2011 by KCB something that looks or matches what these guys are reporting. And KCB did a lot of transects. They went round the dam running perpendicular transects into the tailings pond. At the time, they didn't have any barges, so they only were working on beach above water sands. So and they went out as far as the driller could go on the beach. So this is the cross section you're looking at, and there is 4 CPTs as you can count. This black line here, that is a recently built cell, so that kind of corresponds to this here, and that then is a previous cell, and then the dam will slope off to the right of the slide. So that's our compacted cells in here. The orange is the location of the tailings. So you can see now we're going upstream onto tailings here. And we were looking at these various transects, and this one here, you can see we've got a kind of a dense layer here and a bit of a dense layer there, and somehow over there we said, well, this is a passable capture of what the Plewis et al. Paper was suggesting was present at Tar Island. So we said, okay, we're happy with this. This is a reasonable transect, and we will adopt this. Now, in terms of distances, up here I have given the distance between the various CPTs. So we bear in mind that the guys reported that the deformation extended more than 200 meters upstream of the crest. Well, you can see here I'm covering about 200 meters here, because there's my cell crest, and I've got some more information back in here. So this is our piece of information we brought from the later part of the Tar Island construction. And said, okay, this is our engineering judgment as a reasonable characterization of what might have been present in the day 40 years earlier. Now, if you look at that cartoon, it's A over B. You know, we've got a very clear break. What you see in reality, this is one of Ed's photos, is, as you all know, when we spigot tailings, it's like a delta deposit. It's not a uniform sheet, and far from it. So the fact we have variability is really no surprise. That's just reflecting the deposition conditions you can see there. So what we're going to do about it? Well, we've got to process that, and I promised I'd tell you why the simple exponential relationship is theoretically expected. And the basis for this is cavity expansion theory. Now, where does cavity expansion theory come from, and what does it involve? Well, the reason you see a battleship in the top left here is, as in many things, it's the military that have driven technology. And this in the earlier 20th century, when they first started building battleships, they rapidly ran into troubles with the guns, and they wanted to make ever bigger guns. And we went from a half-ton projectile to a 1-ton projectile in a space of about 3 years. And that projectile, weighing a ton, gets accelerated from at rest to Mach 3, or in excess of Mach 3, in about 15 meters. And to do that causes enormous pressures, or that requires enormous pressures. And there was considerable concern about various powers at the time of not having guns particularly explode, but they didn't want the guns to wear out. They wanted the guns to continue to shoot. So a lot of money was put into understanding how metals responded under internal pressure. So when we talk about cavity expansion theory, originally the cavity was the bore of a battleship gun. And the neat thing about cavity expansion theory is it's symmetric. So we can do everything in terms of radial strain. And what you find is if you increase the cavity pressure, so here, if you will, this is the bore of my gun, and I'm magically increasing the pressure so it expands outwards, that you get a cavity pressure, cavity displacement curve that looks like this. And you come to a limiting pressure, which is called the limit pressure. And at that point, the cavity expands by that limit. This theory was developed in the largely in the 1930s, and it started out with say cylindrical cavity, which is the guns, but mathematically it's very easy to switch to spherical symmetry. So if you will, our cavity now is a microscopic dot in an infinite medium, and somehow we have a magic pipe which we can inject pressure into there to make the cavity expand, and you get the same shape of curve. And in the 1940s, during the ramping up of industrial production in the war, they started being more scientific about metal forming. And they found, or they came to the view, that the limit pressure of a spherical cavity was related to the punch indentation pressure required to form metals. And that's where you get further interest in the theory. And that resulted in this paper down here by Bishop. And this is not Alan Bishop, it's a different Bishop. And the idea was, said, well, that limit pressure here, we have a punch going into a metal. That limit pressure here is related to the pressure acting on the front of the punch. In fact, you have to introduce a coefficient because it's an analog, it's not an exact solution. So you get a coefficient there, just like you have a coefficient of discharge in a weir flow equation. And you'll notice here, I've highlighted the word pile, because this was picked up by the civil engineers after the war and said, okay, we can use this for pile design, because a pile is not much different from a punch indenter in a factory. And this is the basis of our pile design codes today. It's cavity expansion theory. Now, CPT people, we said, okay, CPT is just a mini pile. We'll pick up the same thing. So that's where our interest comes in cavity expansion theory. Now, let's go a bit further. The simplest possible reasonable model for soil strength is this one here, which is that phi dash is critical phi cc, plus dilation. Now, this is derived by Peter Rowe, theoretically from micromechanics. Malcolm Bolton, bless his heart, said Rowe's equations are way too complicated for practical purposes. We can just put a coefficient in here of 0.8, and that is as good as Rowe's very fancy theory. The nice thing about cavity expansion theory, I've alluded to its symmetry. Well, and the nice thing about this idealization, it's also quite simple. The two simple ideas can go together, and it allows us to do closed form solution. And the cavity expansion solution in closed form was done by these guys out of Australia, Carter, Book, and Young. And what they did is they combined this with the cavity expansion, and what we can do is and they got closed form solutions, I shall say. And what we can do, we can take their solution, say, okay, if I look at the cavity pressure, and I can look at dilation angle, I get this behavior here. Not quite a straight line, but very close to it. Now, there's also a theoretical relationship between, and this, by the way, is a non-associated Moore-Coulomb model. There is a theoretical relationship between dilation angle here and the state parameter. And it depends on this property chi, so we get a slightly different value for chi of 5, 4, or 3, but it's a one-to-one mapping. And we can combine that with that, and we get this. And you then see we have these solid blue lines. That is what we get by combining the two bits of theory. The dotted lines behind it are the exponential QP equals K exponential minus M psi. That's the dotted lines. There are semi-log things. And you can see this semi-log is not quite perfect, but it's a damn good fit. So when I say I've got a theoretical expectation, I'm playing slightly the role of a consulting engineer, like Malcolm Bolton was over here saying it's a sufficient approximation for engineering purposes. That's where it comes from. Now also notice there are 3 lines, and I plotted them for different values of rigidity. In this model, G is not G max we measure with a seismic cone. It's actually the secant modulus to peak strength. And what we're seeing here is the effect of plastic strain. So if you've got a very soft material which yields quite easily, you get a lower value of cavity pressure, but you always get close to this semi-log relationship. So that's a theoretical basis. Now, we have to then deal with the thing, well, cavity expansion theory, we've got our scaling factor missing. Where are we going to pick our scaling factor up from? The way we do that is and this is us as an industry, this is not particular to the industry in Calgary, what we do is we build giant triaxial tests and we push the CPT into it. So what you're looking at here, this is actually in Calgary. This is the old Golder lab in Calgary, I think on Farrell Road, as it was then. And we have a tank, which is about, by memory, 1.4 meters diameter, 1.2 meters high, and sand has been carefully placed into that tank. The tank has membranes in there, and we can apply radial pressure and we can apply vertical pressure, and the two don't have to be the same. So we can take up a piece of sand at a known density and we can stress it up to whatever stress we want to, and that in there you see is a hole on top of the tank. That's a regular CPT going into the tank, and there's our chap doing the data logging. And if we do a bunch of tests like this, we can say, okay, for a particular value of void ratio, and we've actually turned it into the state parameter, so because we've tested the CSL of these things. So here I'm plotting the characteristic penetration resistance we actually measure when we push into the tank. Here will be a test done at, say, 250 kPa confining stress, and we play. This is quite a loose one, so the state parameter is minus 0.06, and we've left. This is one of Ken Bean's figures. We left the minus sign off it to make the diagram simpler to read. What you can see, you get nice radial lines, and not only that, the slope of those lines is the parameter Q, and if we plot it up in Q versus state parameter on the bottom, and there's our theoretical curve of what we expect it to be, and there's the data, and it's lovely. So we've now got ourselves M and K, and we actually did this for oil sand tailings. It actually was from Mildred Lake. It's not from Tar Island. This is a same tank. I thought I'd use this color photo because it looked prettier, but I'm afraid slides don't scan that well. And these blue dots here are the results of those tests there. You'll also see on there, I'm saying numerical using soil properties. I'm going to explain what those are in a moment, but in fact, we actually used for our calibration for Tar Island, we actually went with the numerical values. Why did I do that? Or why did we do that? Well, there's yet more, because cavity expansion doesn't have to be restricted to non-associated Moore Coulomb model. You can do much more with it. And we, and this is the real we because it was Dawn who did the work, we programmed, wrote a custom finite element program. And the nice thing about cavity expansion is everything moves radially. So you can do a moving mesh solution, and you can move the mesh basically with gay abandon, and nothing gets in the way of each other. So it's very easy to do a large deformation analysis, and you have to do large strain because if you don't, you won't get a cavity limit pressure. You have to worry about things like advected, because when you move a mesh, there's loads on the mesh. You've got to deal with advected stresses and advected work. And what we did was the dots here are tests reported for Chino sand, and that's by far and away the most comprehensive set of calibration chamber data. And so that is the calibration chamber's results on Ticino sand. And we know what this, again, we've tested the CSL, so we know what the CSL is. We have determined the properties of Ticino sand, that is M, N, Chi, the whole 9 yards, just as I showed you at the beginning of this talk. And we then use this spherical code to compute the limit pressure. And that dot there will correspond to this square down here. So for every one of those triangles, there's a thing here. Then CQ is simply the ratio of the average trend line to that trend line. So that's how we establish CQ. And what we can do with that, we can then now go further. We say, okay, how does the K and M change with H, the stiffness? How's it changed with the critical friction ratio? How's it changed with Chi? And we can run a whole bunch of things like that. And what we can do originally back when we did this paper in '98, we did parametric simulations. But as the computers got faster, we said, to hell with parametric simulations, let's just hand out the code. So this code became bundled into a little application that you can run. And effectively, it's a numerical chamber test. And that's known as a CPT widget colloquially. And that is running the CPT widget for the properties of Mildred Lake sand. And that's how we picked up the K and M values. And you'll notice there's an effect of an effect of elastic shear rigidity on K&M. Right, let's go forward. So far I've talked about Ticino, and we actually, at the end of the day, we also ran it against Hilton Mines tailing, which is the biggest outlier in the calibration chamber. So we thought we'd covered off the idea that CQ was indeed unique. But really, you'd like to do better than that. Mason Gafghazi, and this is a part of his PhD work, what he did, he took this whole methodology, thought, well, I can apply it to the worldwide database. So this is one of Mason's figures. He dug up 331 calibration chamber tests on these different sands. Now, each one of these different sands has got a different CSL and different properties, so he calibrated for each of those materials. Now, what we're plotting here is truth, the bottom. So for each of these calibration chamber tests, the various laboratories doing the testing have reported they put in a particular void ratio and they can find it at a particular value of P. And when they tested it, they output a particular value of QT, tip resistance. What Mason has done, he said, okay, I know from the E&P and the fact I've measured the CSL what the state parameter is. That's how he's got the state parameter for that test. He then has taken the QT that they have reported. He's put the QT into the widget. So he's run the widget for the various, if this is a diamond, that's Hoxsand. He's got a calibration for Hoxsand. So he's run the widget using Hoxsand calibrations, put in that QT, turned it into Q, and said, okay, I've now got a state parameter calculated. So we're comparing the entire inversion process here. So truth is what the lab says, and this is what we get from the full inversion. And the diagonal line at the center is a one-to-one equivalence. And what we have here is 80% of the data lies within a state parameter of plus or minus 0.04. I think, and this is back to my engineering judgment, most of this scatter is actually lack of experimental precision with this chamber testing. Now, if you look at our literature, we treat chamber testing as the gold standard. But that gold chamber you saw, that takes 2 tons of sand. It's a pretty big ask to get to an accurate void ratio of 2 tons of sand. And you can look, in particular, the 2 tests I've highlighted here are Ticino E139 and Ticino I169. Those 2 tests have almost identical E0 pairs at 3 significant figures. And yet the reported QT differs by a factor of 2. So that is an example of the precision in chamber testing. And what I observe, and hopefully what you agree with, is pretty much most of that scatter is attributable to experimental precision. So my view, and those of us who like the widget, is that actually the widget is optimized across the entire world's database. So we rather like the widget better than particular individual chamber tests. And that's why we went with, back up here a couple of seconds, so I can catch you. Yeah, that is why we went with the numerical results rather than saying, okay, we want to hang our hat on the physical chamber tests. You can see that we're not a million miles apart. It's just we believe, a much better definition of the inversion parameters Km from the widget from fiddling with the chamber data. But one further thing that leads me to believe the widget is our best estimate at the moment for getting to the in-situ state. This is the Cadia dam failure, and you can see the liquefaction here. And what was unusual about Cadia was we actually had a CPT in the soil that subsequently liquefied a year before it liquefied. And of course, as you all know, when we have one of these large failures, there's always a search for the guilty. So you convene an independent review board to find out what went wrong. And we got hold of the digital data from that CPT and we processed it as I've just described to you. And we produced this line here showing our estimates of the in-situ state. And the reason it's not a continuous line is because it depends whether it's drained or undrained. So We don't use a drain calibration if the part of the sounding goes undrained and vice versa. So this is the bit was relevant to what I'm about to tell you. Now, the engineer of record of this dam of ATC Williams, bless them, they had done some very high quality piston sampling. At the same time they were doing the CPT soundings. You can see the sample you can see down here. You can see our flagship sampler and the blurb around how good it was. And bless them, they had sent a memo to Newcrest documenting the density of the soil recovered in those tubes, and we did as a board. We didn't know about that when we ran our predictions, which is why I'm calling this a Class B validation. Because what we as a board had also done is we'd looked at these tailings and we said, well, there's a predominant type of tailings and there's some sort of sandier interlayers. And we determined the CSL of both of those materials. And we could then say, well, if I know the density of the tube and I know I can turn that into a void ratio because I know what GS is, I don't know whether that tube contains all of the predominant tailings or whether it's probably not all of the sandier tailings, but that's my uncertainty band. So I can say, well, I can calculate my state parameter from this information. And that bandwidth is the state parameter from this program. And I was flabbergasted when this came up. And I say it's only Class B because the data existed before we made our prediction. We didn't know about it. And that really pushes me into thinking, actually, with the widget, we're doing pretty well. And we prioritize the widget over the direct physical calibration chamber tests. Well, back to let's now process the data and see what we're dealing with for our Plaxis model. This is the figure I introduced you earlier on why we selected this transect. We're now going to process these samples, and we're only going to look at the beach, these three here. And what we get when we process it is this. Here's our state parameter, and there's my three CPTs. So the orange one is 100. That's probably this one over here. 101 will be that one there, which is the blue ones, and then the dark green one will be the one who's now behind the slide. And at this point, you say, well, that's a bit of a muddle, Mike, isn't it? You've gone taking us through this great story about theory and how we process and so forth, and what on earth have you got? What on earth are you going to use in a finite element analysis with that kind of scatter? Well, to answer that question, I have to take you from Alberta across the pond, and this is the Netherlands, and this is the Oosterschelde barrier. What you're looking at here, this is a storm surge barrier, or the Eastern Scheldt storm surge barrier, and these are concrete caissons with gates to shut out storm surge when you've got a high surge in the North Sea. And these concrete caissons and their gates are actually founded on a hydraulically placed sandfill pad underneath them. So they put a sandfill pad down and leveled it and then drop these concrete caissons on. So the question in the day of how stable these caissons would be under storm surge loading and large wave loading that might accompany storm surge conditions in the North Sea. What they carried out was a bunch of centrifuge testing. And the centrifuge tests, they actually, as you can see here, this is the footprint of one of those caissons, and they put little loose pockets in it because they were well aware that hydraulic fills weren't necessarily that uniform. So they came up with this regularized lack of or non-uniform thing of loose pockets, and that's it in section and that's it in plan. And they ran centrifuge tests. And what they discovered was the loosest 10% of the ground pretty much controlled the response of their caisson to storm surge loading. Now, I need to take you away from the Netherlands back to Canada, and we're now up in the Arctic. This is the Gulf exploration structure. This is not a badly designed ship. This is actually an oil exploration platform. We're about 75 kilometers north of the Canadian coast in the Northwest Territories and in the Beaufort Shelf. We've got ice. This is early in the winter. We've got ice moving past us. And what happens when the ice moves past? It's coming past about 1 knot. It crushes on the front of the platform. And this crushing can go on for hours, and it vibrates the platform. The largest accelerations we measured were in excess 11 G, and we sustained that for 15 minutes. Now, how do we deal with these large loads on a platform? Well, you can't do it with jacket legs. And what the platform actually is a large shear box, and it's full of sand. And in many ways, this platform is a child of the Oosterschelde, because Gulf retained Volker-Steven as our contractor to do the sandfall placement. We have a sand berm underneath her. And along with Volker-Steven, Gulf also retained Professor Peter Rowe. So we have this, this whole Dutch methodology on sandfall placement and sand experience and awareness of loose pockets. And this is the sort of centrifuging that was done to examine the effect of loose pockets. This is the centrifuge in Manchester. This is Rowe's centrifuge. If we go down below, this is Bill Craig, and he's the chap who did the testing for the Oosterschelde barrier I just showed you. And there on the wall of the lab is the Mollek pack. So we have ourselves this awareness, and me as engineer of record, this extreme awareness and nervousness over loose pockets. So what we're going to do about it? Well, that's the sketch of the Mollek pack you saw before, or the model of the Mollek pack. And you look there, you see a bit of space. Well, this slide here shows us working in that space. There's about 3.5, that's the sandfill. So that's the sandfill core. That's the guys are standing on the sandfill core. That there is the underside of the steel girder box deck. And we're cone testing. And we did a lot of cone testing. This is a plot, and the core of the structure is about 70 meters by 70 meters, give or take. I think it's actually 72 if my memory's not gone. Green dots are CPTs. Red triangles are self-bored pressure meter profiles, and that yellow square in the middle is the location of the exploration wells we're drilling to do on our crust. And you can see a lot of CPTs. There's actually 33 of them there. What you can do with that level of CPTs, you can actually start seeing dense zones and how continuous they are. And to see that, we actually had to bring the spacing down, as you can see, to 9 meters. And you can see down here a loose pocket. As I was pulling the slide together, I thought, actually I might have brought the loose pocket over to here. Okay, but we can see loose pockets and their extent. Now, this data set was taken forward by the folks at Princeton. Prevost had one of the earlier models for cyclic loading of sands, and which could run in finite elements. Popescu was the research student doing his PhD on this. And what they did, they took this Gulf data, we shared it with them, gave them all the raw files, and they produced what's called a stochastic model. I'll go back here. Oh, sorry. If you look at the top of the screen here, this is their finite element model. It's basically a square box, and they've got 480 elements in there, and they've gone for a 60 meters by 12 meters deep. And they're going to fire an earthquake into that material. And the shading in that box represents the distribution of loose and dense zones you see over here, except we made it a continuous function. So the dark is the more dilatant material. The white is the more contractive material. So this is an example of what they've implemented in their finite element model. So we've got complete variation of soil density across the mesh and with depth. And we've picked up an arrangement of things. Now, what they've then done, and that's called a stochastic model, they've then run the earthquake into that model. Now, we only know we don't know the details here. We only know the average tip resistance. We know the standard deviation with tip resistance, and we know the trend with depth, and we can come up with the spacing parameter saying it's perhaps 20 meters between or the continuity of a particular dense layer, maybe 20 meters or thereabouts, and we can randomize that as well. And so we have a statistical thing, and we numerically in the computer roll the dice. So what we've done is we rolled the dice and we said, okay, we have a set of populated our finite element mesh with a set of properties that matches our standard deviation, our averages and so forth. And we then run the earthquake at it. And we predict this pattern of excess pore pressures. So the excess pore pressures are now scaling. So when you're dark black, you've got full liquefaction. So here we're running an RU of whatever that is, about 0.8 there. And then we do it a second time. We roll the random number generator again. We get a different pattern, still matches our standard deviation, still matches our mean, and so forth, and our scale. And we get a different pattern of excess pore pressure. Do it a third time, and you can see here, these are called realizations. I've got 6 realizations, and I get different patterns of computed excess pore pressure, but each of those matches my statistics of my CPTs. Right, so that's the uncertainty, what we might have happen to us. Now, as engineers, you and I know we're going to represent the domain as having uniform properties everywhere. So as a second set of simulations run, and now rather than that being having the detail, it's all the same. But here we put in the average. So this is equivalent to saying, okay, we'll have a trend removed average state parameter everywhere. Here we're going to have the 50% of the, we're going to pick whatever the state parameter corresponds to 50% of the soil is looser and 50% is more dilatant. Here we're going to have 60% more dilatant, 70% more dilatant, 80% more dilatant, 90% more dilatant, but in each case uniform. And it's now a question of engineering judgment, because this is how we're going to use our standard engineering calculation. What of those do you think best represents what is in the blue? Now, to my eye, and you can debate this with me later, if I was picking the 70th percentile, I'll say no. I've got, 4 of my 6 cases here are clearly worse than my 70th percentile. If I go to my 90th percentile, really nothing up here is as bad as what I'm computing with the 90th percentile. So as a reasonable engineering judgment, an 80th percentile is not bad. And that's where we landed. So let's now go back to our muddled CPT record, which we've processed carefully using applied mechanics, and let's put that judgment in. I should say here now that this concept of what represents on a uniform domain, what you get in stochastic things, that is called the characteristic value. And in Eurocode's parlance, the subscript K, which I'm highlighting here, is reserved for characteristic values. Now, that was the judgments we made. And we said, okay, and you can debate with me and say, well, I might want a bit to the left, a bit to the right, but that was the judgments we made for this case histories. Originally, I wanted to go with a little bit over here, and it was I suggested 0.065. And my co-authors probably properly said, Mike, you're full of it. You do not have 3 decimal place precision on this kind of judgment. So we actually ran with 0.06. So that's what we put into our Plaxis model. Now, there's a final thing in our Plaxis model we've got to set up. We're doing stress analysis, so we have to come up with a starting stress state in the tailings. Bless them, Clone, Cripp, and Berger have gone out with a pressure meter. This is actually not at Tar Island. This is at the Muscat River mine, and there's our lad and that's our self-bored pressure meter. And we have pulled off the K0 from the self-bored pressure meter, and the way we've done it is this. The blue is what has been measured with the pressure meter. And we've pulled off the elastic modulus. That's just a simple fit to an unload reload loop, which is shown in green. The red line is back to our friends Carter and co-authors, their cavity expansion solution. And we have actually scaled it because the pressure meter is not an infinite cavity. It's got an LOD of 6. The folks at Newcastle used in Australia did a lot of testing with different geometry pressure meters to come up with correction factors to go from the true cylindrical cavity solution to a real pressure meter. So we've put that in, and we've also run it with large strain mode because the Carter solution is. And we've then adjusted or guessed K0, and we've guessed the dilation angle, and we compute a solution, and we look at the computed solution, compare it to the measured data, and we then update our guesses. It's called iterative forward modeling. And what we're doing is optimizing the model against the entire data set. And that enables you to pick, because the whole solution scales with geostatic stress, so we don't have to try and identify what a K0 is from the data over here. We can pull it from the whole curve. And that's what we've done. And this is what we get. And this is the example of geostatic stress. And these are the individual pressure meter tests which have been modeled as I've just shown you. And this is the inferred geostatic stress case. What's intriguing is this stuff here is primarily in the dike crest, an area that's being tracked with dozers. And the offset is almost like a dozer pressure. It's about, numerically, it's 60 kPa, and that's very similar to what's published for the dozer D10 track pressure. But what we went with said, okay, we're interested in greenfield tailings away from the details. Whoops, sorry, wrong way. So we adopted this baseline trend as for both the beach above water and beach below water tailings. We went with a K0 of 6. So at this point, we've got our cell model set up. We know, and this is the schematic of the Plaxis model. This is in purple. That is the rays we're going to build in the computer. This is our beach slope, and that is beach below water there. That's beach below water here in light blue, and that green layer is the layer, what we call layer AA. This is the layer flagged up in the Plurs et al. Paper. We're saying, well, we've got ourselves a potential relic beach in here, and that's what we've put in. If we look at the details, there is no description in the Plurs paper about how they actually got onto the surface of beach below water. And I don't believe you can, from what I've seen on other sites, you can drive on a dozer on beach below water. So I think they must have put some sort of beach above water layer in there. We call that a mat. So we put a little bit of a mat in there because we felt that was needed to make the construction sensible. We also wanted, you've seen Bob Hardy's sketch to the failure, and it drops vertically. We wanted to get a weak layer in there to try and make sure the thing dropped properly. We're also interested now to understand how the liquefaction evolves. So point A was the point there in the Plurs paper. They identified point, and they did a back of the envelope calculation of stress paths. We didn't think liquefaction would start there, so we picked a point B, so it's nearer the toe, because we thought that's where we might see action first. And of course, we want to know what happens out in the green field. Bear in mind, they said this thing punched out 200 meters. So we said, well, let's track what's going on in C. So that's our model, that's our idealization. And of course, in a case history, there are uncertainties. So the base case is basically what I've talked you through. We have this layer AA, and remember I showed it's a little bit denser, so we stuck in a state parameter of minus 0.02. The plus 0.06 is the beach below water, and so what I've talked at length about. And we put in Gmax at the SCPT trend, which I introduced to you earlier in the beginning of the talk. We wanted to put in some different views, and so base case is our best shot at capturing what we find in the Plurs et al. Paper. But for scenario 1, we said, well, if we look at the photograph, particularly Ed's photograph of the time, we see a delta deposit. And the idea we have this clean, simple beach above water which has been submerged, it might be discontinuous. So we simply removed it from the model. We said, okay, we're going to run without any beach above water which has been buried. We'll just have beach below water everywhere. There was also the concern that perhaps our interpretation, remember I was showing the judgment of how we were picking the characteristic value off of for the beach below water, and there's a lot of scatter in the data. So we say, well, To be fair, perhaps we are being a little scared and we're being talked into or talking ourselves into being too pessimistic or too conservative. So let's make it slightly less dense. So that was denser beach below water, and we brought the state parameter up to plus 0.04. We then said, well, what about, and I'm afraid there's a typo here, this should be thicker beach above water. Rather than putting that layer AA as 2 meters thick, we said, well, what say it's much closer to the very deep layer that you might infer from the schematic in the Plewis et al. Paper. So we stuck that in as 5 meters thick, which was scenario 3. And then scenario 4 was softer elasticity. You find if you try and fit seismic moduli to undrained laboratory triaxial test, it doesn't work at all. You have to bring the modulus down a lot. So we said, okay, we're going to use, for scenario 4, we're going to use the softer elasticity that we find we have to use to match our lab triaxials. So that was scenario 4. So last point is, okay, what about this drain to undrained transition? We have this is the repeat of the cartoon or the schematic I showed you earlier, the figure earlier from the guys in the day, the engineers of the day, using controlling construction through a rate of rise and keep themselves out of an undrained transition. And this is the trend line in detail pulled from the Plewis et al. Paper, and that averages out of a rate of rise of that. And we said, okay, if we take a characteristic drainage distance and we take a characteristic hydraulic conductivity, which we'll pull off from Hazen's formula, and if we look at a compressibility, which was not going to be a million miles removed from lambda 10, we can calculate a CV, and we can work out a time factor. And a time factor of 1 is more or less no excess pore pressures, drain loading, and that on that basis that calculates out to 1 month. And you can see here we've taken about 3 months. So there's every reason to think that the empirical rules or the rules they derive from various test fills over here actually made a reasonable sense, but we didn't run a bioanalysis or a consolidation analysis to substantiate the estimate. We said, no, this is good enough, but now we've got to put on a perturbation to see what happens. So we did the last 500 millimeters of the raise undrained. So we said, okay, we're going to ramp it all up drained, and then we'll for the last lift, last half lift, we will just do it undrained. In reality, the perturbation at Tar Island, anecdotally, seems to be the same as I showed you from the site over in Portugal. It was a dozer working on the surface that seems to have caused the vibrations or the unequal loading that somehow triggered the event. Anyway, so I've taken you through the analysis. Now let me show you what we get with Plaxis and the thing. What you're going to see when I run the video or the simulation, you'll see the construction happen over here. So you'll see the raise being built. The color contours you're going to see are contours of eta, the mobile stress ratio, divided by m. And the reason we do that is that we're running with 3D stress and strain invariants, and there's an effective intermediate principal stress. And there's also m varies with intermediate principal stress, or proportion thereof. But the beauty is, if you run with the ratio eta over m, those two factors cancel out. So that ratio means the same in plane strain as it does in triaxial. And more the point, a value of 1 corresponds to soil in the critical state. So when you see it flash to red, that is where the material has gone into its critical state. So with that ado, let me start running this, hopefully run the simulation, see what goes on. Here we go. Bang, we've got interliquefaction now, and watch it propagate. And see how the crest is now starting moving downwards. Let me run it again, so it ran quickly. Okay, so That's kind of neat, isn't it? When I first saw that, I literally just about fell off my chair. That was, when that first appeared on Dawn's screen, I thought that was staggering. Okay, I want to, hang on, I don't want to do that. I want to move ahead here. There we go, next slide. So what's going on here? At the onset of liquefaction, you can see it triggers down here. And with liquefaction fully developed, we're down here. This is Bob Hardy's sketch of what happened on the day. On the base case, we get about 4 meters of settlement here. If you look at this honestly from thing, he's got about probably about 4.8 would be where you might characterize that. So we're not quite getting the thing there, but you can see we're hanging up at the back here. We were not able to make a tension crack happen. We have 500 millimeters of movement way out there. So entirely consistent with what they reported in terms of the extent of liquefaction. Now, how is this occurring? What are the tailings doing? What are we computing here? I'm showing you the end result, but what is going on internally? Well, remember we had the marker points A, B, and C. This here is now the stress path at the marker points and the stress strain behavior at the marker points. B here, this is us loading it up drained. And when we go to undrained, it has absolutely no reserve of strength whatsoever. So the moment we put an undrained perturbation on it, you can see here the stress strength drops, and you can look at over here, it's absolute catastrophic drop of strength. So that has to throw, when that first liquefies, that has to dump load. The load gets shed both directions. A, initially, when we put the undrained load on, there's got a reserve of undrained strength over here. But as that one dumps load, B dumps load, the stress on here comes up, and then bang, that one comes down. And then, of course, a little bit later, C gets into the game and comes down. What's interesting is if you look at the residual strength ratios, they differ a lot. 0.1 at A, 0.14 at B, and 0.04 at C. And the reason for that is when we're building it, we're building drained. And we've had a lot of, for want of a better phrase, consolidation from the weight of the fill. So the void ratios here have changed significantly, and that has changed the strengths. Over here, we're on the greenfield condition. If we look at the various scenarios, how they have come together, this is looking if we had a perfect settlement plate on the top of the tailings just underneath the mat. And this is the settlement you would observe from the various scenarios. So as we're loading up, it's all very stiff until we put on that last perturbation, and then it goes pear-shaped. The blue is our base case scenario. This one here is when we take out the layer AA and just make it completely, or pretend the layer A is discontinuous. The actual is, say, my judgment on Bob Hardy's sketch of the day is 4.8 meters. The green scenario is where we put the elasticity softer. That one over there is 2, which is when we made it denser. And really, I think the reality of this case history, we're somewhere between the base case or possibly not quite as bad as the completely discontinuous there. But one thing I want to bring your attention to this is if you were running the observational method, you might have looked at the plate and you'd say, well, I can establish the initial response, the initial gradient, and then you find it's stiffening up. And you would have concluded, well, I'm running the observational method. Hey, guys, it's getting better. And you would say it's getting better until the moment it failed. And the observation method on these sort of liquefaction things is frankly dangerous. Now, the one thing that really surprised us was when we put in the soft G. And remember, soft G is what we have to do to really do a good fit to lab tests. And we simply just could not get the correct mechanism with soft G. So, this is the same state parameter and the same H's and K's and everything else. All we've changed is the G max. And when we're running the base case, we get this massive kick out, which corresponds to what we have here. We put the soft G in, it just isn't there. And that was quite a learning for us. I'm not sure we fully understand the implications of that as an industry, but that's what we got. Now, there are 3 corollaries of this case history, and I'm now departing from the written version of the paper. And the 3 corollaries are, what is the validity of limit equilibrium methods for assessing liquefaction? a number of people when I have commented on say, well, why can't we just simply use an SU value when a limit? Okay, we may have to do some effort to calculate it. Perhaps you want to use the Olsen correlation because what he calls is the yield stress is actually SU. Okay, so that's question number one. Question number two, is critical state theory limited to normal soils? Because what about residual soils, or more particularly, what about iron ore tailings? This Tar Island case, it's a very simple sand. It's got no funny behaviors really. I showed you where the lambdas fit, and the M's and N's are quite normal. And more fundamentally, as a profession, if we're going to switch out of limit equilibrium, how on earth are we going to communicate safety? Factor of safety is looking pretty meaningless when I'm showing you these liquefaction things. So let me address those three corollaries of this case history now. Can we use limit equilibrium? Well, perhaps, but if we're going to do so, we're going to have to use log spiral mechanisms rather than circles. These liquefactions, these we're getting in the simulations, simply are not close to the slip circle idealization. But we're going down this limit equilibrium road. We've got some questions. What are the inputs? SU varies with strain history, equals location and slope. It's not a uniform number. SU depends on kappa over lambda ratio, not just stress history and E. There are things, for example, in the Olsen plot, which is very scattered, kappa over lambda is the cause of the scatter, but none of us are measuring that in our case histories, and we need to dial that in. And how on earth do we deal with brittle behavior? Because as you saw in that liquefaction, where it fails, it's not failed elsewhere when it initiates, and the whole thing is a propagation. So if it's a propagating, what on earth is the factor of safety? And so what it seems to me, and this is kind of a personal view now, and this is not my co-authors, you're going to spend a lot of effort fiddling with strengths, and nothing will be at face value if you're losing limit equilibrium things. And thus it seems to me, it's just easier to use critical state theory in numerical analysis, because hopefully I've convinced you, as I've led you through how we made the judgments, how we processed the CPT, how we've tested the soil, how we determined the parameters. It's actually a very easy process. It's far from rocket science. Okay, you may not be familiar with some of it, but it's not, as I've hopefully demonstrated to you, it's a straightforward process. But there's one further thing about numerical analysis, and that's communication. I'm sure every one of you probably watches breakfast TV, and you're looking at the weather forecast. And all of us these days, wherever you are, you'll see computer simulations of how the day's going to unfold. We've got computational fluid dynamics, which is used to compute how the weather's going to evolve, and it's presented to you almost as a video. And it's very easy to understand what's going to happen. Well, that's what we have with the ability with our numerical methods now. Now that animation I showed you, it's very easy to look at the animation. And you say, look at the animation. Just go look at the safety cam from Brumadinho. It's very easy to say we actually do understand what is going on. And it's very easy to communicate to our stakeholders, be they directly our clients, the regulators, or the public at large. And this to me is one of the great things as we go forward as engineers, was we're now able to do as good a job as TV weathermen or weather ladies. It's not a technical aspect, but we shouldn't underrate the importance of communicating the situation clearly to the stakeholders. And I think this is one of the great advantages of these numerical methods. We can now do things to communicate rather than arcane things like a factor of safety and slip circles, and nobody really understands that. Whereas once you show this kind of thing, it's obvious. Okay, are there some sorts of things critical state theory cannot represent? Well, as you know me, those of you who know me, I'm an exponent of critical state theory. So of course I'm going to say no, critical state theory can do anything. We can represent every material. But let's get a bit more, get a little bit less sales mode, and let's do it more fundamentally. It's really a question of adding detail of the soil physics. Of course, more detail means more properties. That means more work and whatever, but let me show you. One of the criticisms of critical state theory is it cannot deal with structured soils, and residual soils are often offered up as an example of where critical state theory cannot work. Well, what you're looking at here on this slide is the In brown is the measured stress strain behavior and stress path of the residual soils of all the key strain weakening residual soils in the Cadia foundation that caused failure of that dam. In blue is the fit of the critical state model to that test. Now, how have I achieved that fit? Well, what I want you to do is look at this over here on the right-hand side. I have drawn the green M line through the endpoint of the test. So, okay, there's my stress bar. You can see it sliding down. That is my phi C or my M, my critical state friction ratio. And now if you project that line up to here, look where it crosses the brown line. Now our basic stress to latency equation is this, dP equals M minus eta. Well here, if that is M, then I've got eta equals M, and so there should be no dP should be 0. Well, if dP is 0, the stress path should not be bent to the left, it's bent to the left because dP is positive. dP can only be positive if M is actually greater here than it is down here. So how did I get the blue line? Well, I took that idea and we just do that too. We put in a structure, said, okay, MD grade has a intact value up to the strain, and exponential. Looking back to, back to here, you can see that 3% kicking in there. Perhaps I should have made it 4. But you can see the idea, and it's a very easy add-in. And it's true. Now, a little bit more, and go back to look a bit more fundamentally, and let's go back to Bishop's procedure. Don Taylor introduced the idea that we need to correct for energy in a shear box test. And I've got over here a picture of a shear box, and you can see easy enough, we've got a dense sand in here, and it's dilating. That top platen is going to rise up. As that top platen rises up, it's going to lift a weight. So it's doing work. And so in the day, they call this an energy correction. And what Bishop has done here is one of his shear box tests, and that's a loose shear box test. He's got 2 tests, and he's applied the Taylor energy correction to compute what he calls the internal friction, which is what we would actually call M. And what we do these days, we say, okay, it looks like M is a constant, or in the textbook, we say phi C is a constant. And that you'll find in pretty well, all textbooks. Phi C is treated as a universal constant. But look carefully. Look over here. You see that when we apply it, phi crit or phi CV is not there. It's down here. The energy correction. Now this is data from 1950. Here's some more modern data. Brown is one of our tests. And we've got exactly the same as what Alan Bishop had in the shear box. Yes, the idealization of constant M isn't bad for the test as a whole. But look over here, it's very poor in the first 1%. More interesting, this in blue is iron ore tailings from Brazil. And there you can see a very slow evolution. It's like we took 1% here. This is now taking 10%. Add this detail in if we wish, but it's not a blocker. More generally, if we're looking at structured and bonding and crushing soils, we probably have to deal with an evolving M. It's possible with crushing soils that the critical state line may also evolve with strain. And we may also want to introduce creep. I know Brumadinho, they've made a big fuss about creep. So we may want to make M depend on time or the strain rate. But fundamentally, what we need to do is not question how critical state theory do it. You've actually got to start saying, well, what is my soil doing? So you've got to process data to stress to latency form to see your material behavior. And then you can add that material behavior into your characterization. Fundamentally, this equation over here on the right, this is what we're involving in critical state theory. We say this is our strain, stress to latency law we use, or our flow rule. And we say the plastic strain increments, or the ratio of them, is here. This represents the dissipation of plastic work. The Schofield and Roth idealization was that's the constant. This is they called it M, but there's no reason it should be constant. That can be an evolving term, and that's what we need to modify some of our soils dealing with. Perhaps in our tailings business, we're now in a position that the standard stuff we do with quartz sands really isn't quite good enough. We need to allow for the way the particles are breaking and developing bonds. Okay, communicating safety is my final point. As a profession, there is near 70 years of experience of communicating slope and dam safety in terms of the factor of safety. We've got numerical values of safe or acceptable in our codes, and I guarantee every one of you is comfortable discussing a factor of safety 1.4 versus 1.5 or whatever, and how you calculate it with limit equilibrium methods. But if an equilibrium is unreliable for static liquefaction, as it is, then using it to compute a factor of safety for upstream construction is frankly meaningless. You're just an exercise in deluding yourself. If we're going to go to these numerical methods, we need to get working on building experience base, because over here, on our limit or our basis for geotechnical engineering, we've got 70 years of experience of this and what we're finding now with these big dam failures, we have to do a paradigm shift. We've got to shift to an entirely new way of analyzing things. And we really need to accumulate as a profession a bunch of experience on what the dam looks like. How do these things propagate? What does safety even look like? And then have to communicate these ideas. The folks at Imperial, Dave and Lydia, have made a stab at this with a paper which I've flashed up on the screen here. But as a profession, we cannot rely on one university, however eminent. This is something, I'm thinking of you guys, or myself as consulting engineers, we need to get our heads around this. We need as a profession to start discussing this sort of thing. If you think back when we have sort of paradigm shifts when soil mechanics was developing, we'd have a speciality conference on it. It seems to me we need to somehow, say the Geotechnical Society, pulling something together. We'll get some people in the room, and it cannot just be academics. It must have some consultants involved, where we start discussing what safe looks like. What does unsafe look like? How do we use these methods? What partial factors should we use? And we've got to integrate this stuff into our codes. There's actually quite a lot of work to do. It's not just a question of, let's just run Plaxis, as I've shown you. It's a whole business of communicating how these results are to be understood. In some ways, these analyses like Tar Island or Brumadinho, we don't know things fallen down, so nobody's interested in how safe it was. We know it wasn't. So what I'm suggesting to you now is that actually in front of us as a profession, a large chunk of work done. And we need to do that because that's the sort of the ethical way forward. We need to shift our methods, and we need to build an experience base so we can provide confidence that this paradigm shift is sound and it is reasonable. So that's it, guys. We'll see what we can do with questions. And I put this paper on again to remind you to go download that paper, and you'll find stuff there. So I think I'm stopping screen sharing, and I'm probably back to Will.